Day 25 of getting back into LeetCode. Today I'm going to solve the daily problem 120 triangle. I think I've solved it before, but I'm going to attempt it without looking at the previous solution. Okay, so as usual, let's go through the problem description first. Okay, so we're given a triangle array and we should return the minimum path sum from the top to the bottom. For each step, you may move to an adjacent number of the row below. More formally, if you are at index I, on the current row, you may move to either index I or index I plus 1 on the next row. I see. So this is how the triangle array looks like. So we can, if we are here at position 0, we may move to position 0 in the next row or position 1. Okay, so the left-hand side is always index 0. Okay. The next thing that I always do, and that's what I would do in an interview, is look at the constraints or ask about what the constraints are. In this case, the size of the triangle array is limited, but there's at least one entry. That's good to know. And well, at least this means there's at least one row. And this means that there is at least one entry per row. Okay, cool. And and then we also have a condition on how large the next row is, and it's exactly one more than the previous row. Nice. And the values in the triangle are also negative to positive numbers. Okay. So potentially we might want to find a path that goes through negative numbers. And yeah, okay, I think that's everything we need to solve the problem. But okay, let's just go through an example. That's always a good thing to do. So we are giving this triangle array and it's represented like this. So what would be a minimum path? Would be from top to bottom, from 2 to 3 to 5 to 1, which would be 11. Okay. So if we move from one position to the next position, if we are at position 3, okay, so the way I would look at it is, if we want to determine what the path sum is to 5, we want to choose the minimum path sum from the two predecessors of 5. So if we say from 2 to 3, that is a path sum of 5. From 2 to 4, that is a path sum of 6. So if we want to determine the minimum path sum to 5, we can choose between adding 5 to 5 or 6 to 5. And yeah, if we break the problem down like this, I think it's quite easy to solve. The only thing we need to do is we need to remember the path sum of the previous row in the triangle. And when we reach the bottom, we just look at what is our minimum path sum in the last row. And that's going to be our result. So, okay, so how could we do this easily? I guess something that we have to do is we have to iterate through the rows of the triangle, right? So an triangle. And we also have to have something that tells us what were the path sums of the previous row. So we're just going to use an array for that. And let's see, and we already know that in the end, we want to return the minimum from the last computed path sum. So we return a minimum of that. Okay, so we need to flesh out the details here. So I guess in the beginning, the path sum, there is none. So we have the edge case of the start. So if not path sums, then what we can do is we just set it to row. because the path sum to get to 2 is 2, right? So that's what we'll do then. Otherwise, we need to compute the minimum parent for each element in the current row. So we're going to iterate over all of those elements for I in row, well, range length row. And so now each number has 2 parents, except for when we're on the edge, right? The 6 only has 3 as a parent because there's nothing here on this side. So we need to take care of that as well. So parents is, maybe we create an array for that. So parents is if I is larger than 0, that means if we are not at the edge, but we were somewhere in the middle or even at the end of the row, then we know we have a top left parent. So we can say parents, maybe I'm overcomplicating this a little bit. Min parent is going to initialize it with infinity. And now we do this. So if I is larger than 0, then the min parent is equal to the minimum of the current min parent, which is infinity in the beginning, and actually the parent. So, and that would be, well, we would use the path sum for that at position I as well. And if I is smaller than the length of the row, -1, then we can also look at the top right parent. So we're here at 5. We know the top right parent would be here where the 4 is. And the path sum to get to 4 is path sums at I plus 1. Now, if we're exactly at the edge, then this will prevent us from trying to access that parent there. So yeah, that should be, let me see. Maybe I have an off by 1 error here. I think I do have an off by 1 error. So 6 has no left parent, but it has a right parent. So the right parent should be at index I, and the left parent should be at index I minus 1. Yes. That is exactly right. And we can make that a little simpler as well. Is larger than 0. I think that is now correct. Yes. And yeah, so now we have the minimum parent, and we know that we can update our path sum. So for the next path sum, I wish I could speak English. We will have to add this to a temporary array. And in the temporary array, we add the current the path sum of the parent to the actual value in the row at that position. So we can just do that, I guess. So enumerate iterates over all of the elements, and it gives us an index for free as well. So n would be the value of the cell in the triangular array. So we have to add the min parent to the value, and that's the current one. Yes, and then finally, we have to update our path sums. I'm just going to set it to TMP, and that should be it. Yeah, that should really be it. And if we're going to step through the debugger in a second here, but let's do a quick runtime analysis first. So we have to iterate over all of the elements in the triangular array, right? So if we say n is the number of elements in that array, we have O of 1 runtime complexity. And we have O of something else space complexity. If we say this triangular array has n rows and n columns, in that case we would say we have n times n runtime complexity and O of n space complexity, because the largest edge is on the bottom, which n elements, and yeah, and we always need to remember n elements at the max. So I think this is a good runtime analysis. So where n is the height and width of the triangular array of the, yes. Cool. So now let's step through the debugger real quick. I always recommend doing this in an interview because typically you find an error that you did not spot when you wrote the code. And it's always a good impression if you can find a bug before you try to run your code. So let's see. So we initialize our path sums array. It's empty. And then we start iterating over all of the rows of the triangle. Now, if we're in the first row, we don't really have a path sums value yet. So what we do is we simply set our path sums equal to row. That's all we do. Now, in the subsequent steps and iterations through the other rows of the triangular array, what we do is we create a temporary array into which we write the updated path sums for each of the cells in the current row, or the next path sums. And after we've computed that, we make sure that we update our path sums array with the new computed one. Okay, so inside a row, we start to iterate over the indices and the values of the row. We have to determine the minimum parent, and actually we should maybe call it min parent path sum. Min path sum parent maybe. Maybe that is a little bit more expressive. So what we will do is, if we are not at the edge, that means we can access the previous path sum array at position I-1. So if we are at position I equals 1, we are able to access I-1, which would be the 0, in the previous row or in the previous path sum array. Now the other edge case is when we are at the end of the array. This is when the value I is smaller. Well, if it's equal or as large as the length of the previous array. So here, this the path sum array for this row would have a length of 3. So if we go to index 1 to 3, then we are able to access the index 3. Now I see that here I have a mistake. So this should be an equal, right? Because we want to allow the 3. If I don't allow the 3, then I wouldn't be able to do this. So good that we stepped through this. I could also say if it's smaller than row, doesn't matter, it's the same. But yeah, so this was a mistake. And if we're able to access the rightmost parent, which is this, right? This if case, then we're going to update our minimum path sum parent, potentially, depending on what the value is at that position I. Yeah, and then finally we're going to add the minimum path sum parent to the value of the current cell in our current row. So I hope that is it. I'm now going to run the code, see if it passes the tests. Hopefully we have no errors. And we do have one. So let's see if it's smaller or equal. Oh, maybe I did make a mistake here. So it's very tempting now to just jump into the code and just try different things out. But I would highly encourage you to actually think about what you're doing. So why was this wrong? Length of path sum. So if I'm in row number 0, 1, in row number 2, the length of path sums is 2. If I'm at index 0, 1, 2, oh yeah, so I actually, I thought I fixed an error that wasn't an error, so I made a mistake. I actually have off by 1 error again. Okay, great. Well, that happens, you know. And okay, so that seems to work for our 2 test cases. I'm now going to submit this to see if it passes all of the test cases. And hooray! Yeah, it works. So yeah, things like this can happen in an interview. Don't worry too much about it, just work through it. The most important thing is that you can reason and explain what you're doing while you're doing it. You don't want to leave the interviewer guessing what you're currently thinking. And yeah, mistakes are bound to happen, but you know, that's why we practice. So yeah, thanks for watching this one. I hope it was useful. I recommend trying to implement this yourself. If you look up other solutions, you will probably find something like use dynamic programming, etc., etc. Pretty much what we did here. Sometimes I think the terminology just overcomplicates things. If you look at a problem and can come up with a good solution that is logical, just implement that. And don't worry too much about what the special technique is or whatever. Anyways, I'll stop it here.